Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture, and still welcome to today's lecture. And first, some announcement about assignment 1. So you can check this announcement on Wattle. So basically, you can collect your assignments next week during your tutorials. And also, you can check your grade on Wattle for your assignment 1. So any questions about your assignment? And I'm going to release the next assignment, I think, next Monday, right before 8 a.m. And I think similarly, you are going to have almost 10 days to finish your assignment 2 and then submit your hard copy to the administrative office. So any questions about assignments and about previous lecture? Okay. So that's just to continue the previous lecture. So in the previous lecture, we were talking about how to predict a 3-category response variable. And in this specific case, we consider to predict type 2. Type 2 is our response variable. And type 2 has 3 categories: diseased, healthy, and partly diseased. And in order to predict this kind of 3-category response variable, we propose a nominal response regression model. And the nominal response regression model is a direct extension of the binary logistic regression model. And this is our nominal response regression model. So this is our model. And specifically, we have 3 categories. So in the model, we try to model the probability of each category. And for instance, we have pi1 equals to the probability that y equals to 1, and pi2 equals to the probability that response equals to 2, and pi3 equals to the probability y equals to 3. And this 1, 2, 3 represent diseased, healthy, and partly diseased respectively. And in order to predict this 3-category response variable, we need to model the probability of each category. So that's our idea. And in order to model the probability, here, by considering the similar idea compared to the binary logistic regression model, we model the ratio of those probabilities. Because we are interested in modeling the ratio, so we need to have something at the denominator. And here we consider pi1 as the denominator, and usually we call this corresponding category 1. So here, 1 is the 1 is baseline level. Because the probability of category 1 is at the denominator of the modeling. And you should be very careful here that because now the baseline level here means the baseline level for the response variable, not for the explanatory variable, which is different. And in order to model this ratio, we consider to use the exponential of the linear combination of explanatory variables to model the ratio. So in the previous lecture, I think I have a typo here, not typo. So basically, I made a mistake in my handwritten notes, so I need to have the exponential. And you can see here, because we have 3 categories, so we are going to have 2 equations in this modeling. We have pi 2 divided by pi 1 and pi 3 divided by pi 1. So actually we have another equation, which is pi 1 plus pi 2 plus pi 3 equals to 1, which is obvious, so we do not need to model pi 1. Actually, you can consider here, because if we can obtain pi 2 and pi 3, we will automatically obtain pi 1 by using 1 minus pi 2 minus pi 3. So we only need these 2 equations in our modeling. And another observation here is that because pi 1, pi 2, and pi 3 are our probabilities, so the ratio of the probabilities should be positive, right? So that's on the left side of the equation. And also on the right side of the equation, we have the exponential of the linear combination, which is also positive. So in this case, we have the consistency between the ranges of the 2 sides of this equation. So the range of the left side of the equation is from 0 to positive infinity, and also on the right side of the equation we have the 0 to the positive infinity. So that's also consistent with the idea of the generalized linear modeling. So that's the modeling for the nominal response regression model. And compared to the binary logistic regression model, if you still remember, so for the binary logistic regression model, we only have 1 equation. So this is the binary logistic regression model, pi 1 divided by pi 0. But for the nominal response regression model, we have multiple equations. So that's the only difference. And after we have the modeling, we can have the model fitting by using the maximum likelihood estimation. And then we can obtain this summary output. And in this summary output, we can obtain the estimation. And for instance, you can find those maximum likelihood estimation at this coefficients table. And we can have the beta 20 estimation, which is hat beta 20 here. And what's beta 20? So beta 20 is the, you can consider it as the intercept of the pi 2 divided by pi 1 equation. And the corresponding estimation is here. And similarly, you can find the other estimations. So I have already noted all some estimations for you, such that you can compare. So for instance, we have the beta 36 hat, so which is the estimation of beta 36. So that's the estimation part. Because we have more equations, so the estimation part is a little bit more difficult compared to the previous case. So we have a lot of coefficient estimation. And here, if you count the number of the coefficients we estimated, so in total we have 14 coefficients to estimate in this case. And correspondingly, we can obtain the standard error. And the standard error is provided at this standard error table. And we can obtain the standard error. So if we have the standard error, for instance, we can have the estimation here, and also we have the corresponding standard error here. So by using this tool, we can actually obtain the confidence interval. So for instance, so this is actually the estimation of beta 2, I think. So this is beta 20, this is beta 21, and this is beta 22. So you can obtain the 95% confidence interval of beta 22 is 21.597, maybe 80, minus plus 1.96, which is the Z 0.05 divided by 2. So which is actually the 97% 5 quantile of the standard normal distribution, the quantile times the standard error, which is 3.1163. So by using the coefficient and also the standard error, you can actually compute the confidence interval for each coefficient. And the last one is the deviance. So because we still use the maximum likelihood estimation method, so in that case, we can still have the likelihood. So in this case, because we have a lot of coefficients, so we need to maximize the likelihood with a lot of coefficients and obtain the maximum value of the likelihood, and the deviance just equals to minus 2 times the log of the likelihood. And this value is shown here as the residual deviance. So that's the interpretation of this table. So a lot of comments, so it looks a little bit messy. So basically, because we have more equations, so we have a lot of coefficient estimations. Any questions? So I think you still need more time to process this table, but I think you will get some practice in assignment 2. And let's look at, in this table, we have the coefficient, standard error, so correspondingly we can perform the z-test. However, in this table, it's different from the table in the binary logistic regression model. We do not have the p-value. So in order to have the p-value here, we need to consider some tests. And I think the easiest way in this nominal response regression model here is just to perform the dropping deviance test instead of the z-test directly. So, and also this dropping deviance chi-square test is actually a little bit different. So I need to spend some time in explaining it to you. So I think we have our model, but obviously our model is complicated. So in this case, I will write our model again to help you understand. So our model is pi2 divided by pi1 equals to beta 2, 0, or not beta, exponential of beta 2, 0 plus beta 2, 1, x1 plus so on and so forth until beta 2, 6, x6. So that's our first equation. And our second equation, pi3 divided by pi1 equals to exponential of beta 3, 0 plus beta 3, 1, x1 plus so on and so forth plus beta 3, 6, x6. So I think when you get confused about this nominal response regression model, I think the easiest way for you to understand it is just to write down this model equation. So in this case, we need to estimate all of those coefficients, a lot of coefficients here. So sometimes we are interested in this kind of test. So for instance, we are interested in whether or not x1 is needed in this model when the other variables have already been contained. So that's our null hypothesis. So whether or not x1 is needed. So because the null hypothesis is xj is not needed, so from this model, these two equations, we actually need to test, in this case, if we consider h0 is at x1 is not needed. So this null hypothesis is equivalent to beta 2, 1 equals to beta 3, 1 equals to 0. So because we have two equations, so actually we need to test more than one coefficients. We need to test two coefficients. Because only when these two coefficients are 0, we can have this conclusion that x1 is not needed in the model. So that's the difference between this model and the binary logistic regression model. Because when we consider this kind of test in binary logistic regression model, we only need to test one coefficient. But in this case, in this specific case, we need to test two coefficients. And similarly, if we have more categories, we need to test c minus 1 coefficients. And in this specific case, c equals to 3, so we need to consider to test 2 coefficients. Because we need to consider to test more than 1 coefficient, so what we can do here is just to use the dropping deviance chi-square test instead of the z test. So what we can do here is just to firstly use to load the library car. So before that, you actually need to install this library, but when we consider to compute the VIF, if you still remember, we have already installed it in R. So please load this library and then use this capital ANOVA function, and then this is our regression output. If you just try to use this function, ANOVA function, and then you can get the p-value for this kind of test. So you can see from this table, the degree of freedom is always equal to 2, because here we are testing 2 coefficients. If you still remember, the degree of freedom for the dropping deviance chi-square test is always the number of the coefficients, the chi-square d, and d equals to 2. So that's our number of the degree of freedom. And also, if you look at this table, so basically this table test, for instance, the first row. So what's the meaning for the first row? It tests H0, which is X variable class is not needed. And similarly, if you look at the second row test, X density is not needed, and so on and so forth. So that means each row represents a dropping deviance test. And if you have a look at it, you can find those p-values. So if the p-value is smaller than 0.05, so we can have the conclusion that we need to reject the null hypothesis, and for instance, the density is actually needed in the model. So this is a little bit different from the binary logistic regression model when we are considering to test one variable. Even if we are considering testing one variable, but we still need to test more than 1 coefficients. So any questions? So this is different, please remember. And the next one is to consider the prediction of this model. So in this prediction, we are considering some new explanatory variable. So for instance, suppose we observe a new observation with the following values of X variables. And the question is that, based on those observations, what is the prediction? Of Y. So we need to answer this question. And I received an email from the student, I think basically asked a very similar question. So how these values come from? I think the question actually asked about the multiple linear regression model, but I think that's the similar case here, so I'm going to answer here. So those are just some new observations. So you can consider that you collect more data, you collect more weight kernels, and you find that this is some new observations of the X values. So now you are interested in predicting whether or not this weight kernel is healthy or diseased or partly diseased. So that's the question. So in order to answer this question, firstly, you need to specify a new data frame, which includes all the new X variable values. And you need to be very careful here is the data frame. And I think you have already experienced it. If you didn't specify this data frame correctly in your assignment 1, so you obviously will get an incorrect result. Still, you need to specify a data frame very clearly with all of those names, column names, which are consistent with the column names in your input. So those column names should be the same as those columns, as those variable names in your input of the nominal response regression model. So that's basically the same. Same logic compared to the multiple linear regression model. And then what you can do is just to input the regression result. So that's the regression result. And also the new data here to obtain the predicted probabilities. So remember that our nominal response regression model is used to predict pi1, pi2, and pi3. So these three are probabilities of each category. So what we can do, because we are modeling it, so after we get the estimation, we can actually predict those probabilities based on the new observed x values. So in this case, if you specify probabilities here as the type argument, and you will obtain the probabilities. So I do not remember which one is 1, so let's have a look. So 1 is diseased, 2 is healthy, 3 is partly diseased. So this corresponds to pi1, pi2, and also pi3. So we are going to have the predicted diseased pi1 hat, and healthy pi2 hat, and also pi3 hat. Those are predicted probabilities by using those new values of x. So you can use R to obtain those probabilities directly. And if you still remember the logic in the binary logistic regression model, we usually use the corresponding category which has the largest probability, because we have the 93.7% probability that we have this healthy category for this weight kernel. So obviously our prediction for the response, so this is the prediction for the response, is healthy, because the prediction of the response can only take 3 values: healthy, partly diseased, and also diseased. And because this one is the largest, so that's the logic to use those predicted probabilities to predict the categorical response. And how to do that in R? So the only difference here is just to specify the type as class to obtain the prediction of Y instead of the probabilities. So that's the prediction, which is actually the most important part for this modeling, because if we want to accomplish these artificial intelligence systems to automatically distinguish the weight kernels, you actually need this kind of modeling for you to automatically predict whether or not the weight kernel is healthy. So that's the prediction of this modeling by using R. Any questions? Okay, let's look at a slightly different modeling, but the idea will be very similar. And in that case, I think you can compare these two, and you can learn both very well. So for the ordinal response regression model, so if you still remember, the only difference between the ordinal response and also the nominal response here is that for the ordinal response, we actually have an order. So for the nominal response, we only have the information that we have capital C categories. But for the ordinal response, we have this extra information. For instance, category 1 is smaller than category 2, and category 2 is smaller than category 3, and so on and so forth until the category capital C. So that's the extra information. And because we have the extra information, we can actually compute the probability that the response is smaller than C. So if we do not have this kind of order, we can never compute this kind of probability. So for instance, if you still remember the nominal example, red, yellow, and blue. So that's the nominal example. So for the nominal example, because we do not have a particular order, so what we can do here is just to define the probability pi1, pi2, and pi3, but we cannot compute the probability y is smaller or equal to, for instance, blue. So what's the meaning for it? So we cannot do that. So that's for the nominal response. So that's basically the difference between the nominal. So for the nominal, we can only define the probability of each category. We can never define a probability that's smaller than some certain category. So that's the nominal response. But for the ordinal response, we can do that. So when we do that, we actually involve this extra information in the modeling. So we involve order in the modeling. So that's how we involve the the order information in our modeling by considering this probability, which is smaller or equal to C, and this probability is equal to pi1 plus so on and so forth until pi c. So I think that's obvious because that equals to the probability of y equals to 1 plus the probability y equals to 2 and plus so on and so forth until probability y equals to lowercase c. So in that case, we have this equation. And the next thing is to use this equation to help us to accomplish the modeling. So what's the modeling here? So from this, we can still find that we are still modeling the ratio of probabilities. So these are still the ratio of probabilities. And also, it actually has some interpretation, if you still remember. That's actually odds that y is smaller than lowercase c. So that actually has a name, odds. Remember that in the binary logistic regression model, we have the odds that y equals to 1 here. For the binary logistic regression model, we have odds that y equals to 1, which can be defined as the probability of y equals to 1 divided by 1 minus probability y equals to 1, right? So here, similarly, we still extend the binary logistic regression model, but we consider the odds that y is smaller than c. So that's the difference between this one and the binary logistic regression model. But the concept odds is very similar. And then this model just models these odds as a linear combination of the experimental variables. And because this odds value depends on the lowercase c, so here our coefficients also depends on the lowercase c, but only the intercept. So that's the typical way to model this ordinal response regression model. And also, because we have c values, so what we can do here is just to write down these order equations. So we have the probability y smaller than 1 divided by 1 minus probability y smaller than 1 equals to the exponential of beta 1, 0 plus beta 1, x1 plus so on and so forth until beta k, xk. So that's the first equation. And also we can have the second equation smaller than 2, probability smaller than 2 equals to the exponential beta 2, 0 plus beta 1, x1 plus so on and so forth until beta k, xk. And we can keep on writing until we have the probability y is smaller than the capital C minus 1 divided by 1 minus the probability that y is smaller than capital C minus 1 equals to exponential C minus 1, 0 plus beta 1, x1 plus so on and so forth until beta k, xk. So we have the C minus 1 equations. And the reason why we do not write the last one the smaller than or equal to the capital C equation is that this probability is always equal to 1. Why? Because the probability that y is smaller or equal to capital C just equals to pi 1 plus pi 2 plus so on and so forth until pi capital C, which is exactly 1, because in total we only have C categories. So similarly, we should have the C minus 1 equations. We still do not have the C equations. So that's our models. So you will find that this model is actually similar to the nominal response regression model to have C minus 1 equations to describe the modeling. So we have C minus 1 equations to model ordinal response. And that's totally different from our binary logistic regression model because we only have one equation. And if we have the modeling, so similarly we can compute the likelihood. So what's the likelihood, if you still remember? The likelihood is actually the probability that we observe our observations. So it's actually some probability. So if we can obtain these probabilities, so we can actually compute the probability that we can that we observe, so which is exactly our likelihood value. And if we can define the likelihood, and we can obtain our maximum likelihood estimation. So I will not talk about the details because the derivation of the likelihood is not easy, but the idea should be very similar. And before we actually talk about how to apply the model in the real data, we need to talk about some details about this order, because the order is actually the most important thing for this ordinal response. So remember that what's our order? Our order is diseased is less than partly diseased, and partly diseased is less than healthy, right? So the healthy is the best, obviously. So that's actually our correct order. But if you use this levels function to see the basically the levels of this type 2, so you will have diseased, healthy, and partly diseased. So that means this order from this levels function, so we also have this order of this levels function, is not consistent with our correct order, right? This is our correct order. So this is the correct order. And this is the order from our output. So that means in R we actually do not have the correct order. So what we need to do here is just to transform this type 2 as a new variable which has the correct order. So this step below is just to get the correct order for the response. Because the order is the most important thing for the ordinal response. If we do not have the correct order, it will not return or give us the correct ordinal response regression modeling. So what we can do here is just to use this factor function. I think you have seen it in the previous lecture. Not the previous lecture. I think that's the previous lecture. The very important 4 slides to change the order of the factor values. By using this factor function and input the original response variable type 2, but you need to specify the correct order. So this is the correct order. And if you do that, you can have a look. So now it returns the correct order. The diseased is smaller than partly diseased, and partly diseased is smaller than healthy. So that's usually the most important part here. So in summary, when you need to consider the ordinal response regression model, firstly, you need to get the correct order by defining appropriate variable in R. So that's really important. So that's usually we need to define the order. And also, considering some review, if you still remember, the 4 important slides, if you still remember here. So when we need to consider to change the baseline level, we also need to change the order in R. So for instance, here, we actually, originally we have the HRW as our baseline level, but now we want to change the baseline level. So we also need to use this function, this factor function, to get the correct order. So usually we have these 2 uses, I think, in this course when we need to change the order. In conclusion, the first one is to change the baseline level, and the second one is to get the correct order for the ordinal response. Any questions? So basically, the order is important in R. Please be very careful here. And then, after we have the correct order, so this is the response with correct order. We can use a function which is called POLR. I think it's the ordinal linear regression, and I'm not sure about the meaning for this P. So basically, it's for the ordinal response regression model. And if you want to use this function, you need to use this MASS package. And we have used this package for the variable selection, if you still remember. And also, this package can help us to accomplish the ordinal response regression model. And in order to use this function, it's never difficult. So what you need to do here is just to input the response and also the explanatory variables and also the data, and the method is logistic. So it's still the logistic. Why? Because if you have a look at the probability y is smaller than 1 divided by 1 minus y smaller than 1 equals to exponential beta 0, beta 1, 0 plus, I think it's beta 1, 0. Is that correct? Yeah. Beta 1, 0 plus beta 1, x1 plus so on and so forth plus beta 6, x6. So here we have 6 variables. We can denote x1, x2, x3, x4, x5, x6. So we still have this kind of form. And another form here is, another equivalent form for it here is the g function of the probability that y is smaller than 1 just equals to beta 1, 0 plus beta 1, x1 plus so on and so forth plus beta 6, x6. And this g function here is the logit function. I think gu is the logit function. So these 2 equations are equivalent. It's just some transformation. So because it's still logit function, so that means we are still considering the logistic case. So you can call, even though this topic is called multi-category response regression, or called the nominal response regression, or the ordinal response regression, you can actually call the nominal logistic regression or the ordinal logistic regression, because we still have this logistic function or logit function in our modeling. So that's basically the same. And remember, so here we have the 1, 2, 3. So 1 is diseased, and 2 is partly diseased, and 3 is healthy. So because we have 3 categories, so actually we need 2 equations to describe our modeling. So 1 minus probability y smaller than 2 equals to exponential beta 2, 0 plus beta 1, x1 plus so on and so forth plus beta 6, x6. So usually, if you get confused, so my suggestion is just to write down the model equations. And also, because we have the probability, so in the nominator, we still have the probability of y smaller than 1. But in the denominator, we have 1 minus probability that y is smaller or equal to 1. So that is actually equal to the probability that y is larger or equal to 2, right? Because y is larger or equal to 2 is exactly the opposite of y is smaller or equal to 1. And similarly, we can have this smaller or equal to 2, and this is the larger or equal to 3. So sometimes we also use 1 and 2 to represent this equation, because at the numerator we have 1 and at the denominator we have 2. So for this equation we also use 2 and 3 to represent this equation. So that's just some ways for us to express those modeling. And then we can have a look at our modeling. And firstly, we have the coefficients. So here, if you notice, we actually have the same coefficients for the explanatory variable x. So here, we also have the estimation. And for instance, we have the estimation of beta 1, which is beta 1 hat, beta 2 hat, and beta 3 hat, and this is beta 6 hat. And we can have the corresponding standard error, and I will not talk about it. But here we have something which is called t-value. It's actually z-value, but I think you can consider it as in this package, the author likes to use the t-value. But what's the z-value? Z-value is the standard, is the estimation beta j hat divided by the standard error of beta j hat, and which is used to test H0 beta j equals to 0, right? So here we only have the test statistic, but we do not have the p-value, because it's written by someone, and that someone does not give us the output of the p-value. So for now, do not need to worry about it, because later I will show how to obtain the p-value. But before that, we actually need to talk about the estimation of the intercept. Because here, we actually have the two intercepts, beta 1, 0, and beta 2, 0. So correspondingly, we should have the, so I think I cannot write in this way. I should write here. So that's beta 1 hat, beta 2 hat, beta 3 hat, and beta 6 hat. And for this, we have the beta 1, 0 hat, and this is the beta 2, 0 hat. And why this is beta 1 hat, 0 hat, and this is beta 2, 0 hat? Because in the front, so you have this diseased and partly diseased. Remember, diseased is 1 and partly diseased is 2, so which is 1 and 2. So for the 1 and 2 equation, it corresponds to this beta 1, 0 intercept, the intercept of the first equation. And similarly, in the second row, we have the partly disease, which is represented by 2, and healthy is represented by 3, so that's 2 and 3. So for 2 and 3, we have another equation. So that's our second equation. So correspondingly, we have the intercept of the second equation. So we have the different intercepts for different equations. So that's something you need to be very careful about. So any questions? So my suggestion is just to write down the model. So this is the model. And then when you look at the model, you find that the coefficients for the explanatory variables are the same, so which correspond to this output. However, the intercepts are different. So in this case, we need to be careful to look at this, which one is the correct intercept for the corresponding equation. So here, for the first row, which is 1 and 2, diseased and partly diseased, so we have the first equation. So by using the words here, you need to distinguish which equation it is in your modeling. And Similarly, I think compared to the nominal response regression model, we are interested in testing whether or not one variable is needed. So let's look at this. For instance, if we are interested in testing x1 is needed, so we may consider the hypothesis x1 is needed. And the difference here is that we have the same coefficient for x1, even if we have different equations in the ordinal response regression model. So this null hypothesis is equivalent to, is not needed, is equivalent to beta 1 equals to 0. So we do not have the nominal response regression case. We only need to test one coefficient. So similarly for the other variables xj, we only need to test one coefficient. Because we only need to test one coefficient, we can use z-test, or we can use the chi-square test. So if we want to use the z-test, we need to compute the z value and also the corresponding p-value in the previous page. But in the previous page, the author who wrote this R package doesn't give us the p-value. Unfortunately, you can compute it by yourself, but sometimes it's not that convenient. But in order to perform this test, alternatively, you can use the chi-square test. And how to do that? Still use this capital ANOVA function and also the regression output. And in that case, you are going to get the p-value for the test. So similarly, the first one is to test x1 is not needed. And the second one is to test x2 is not needed, and so on and so forth. And you can obtain the p-value. And if you still remember, the chi-square test in the generalized linear model is actually equivalent to the z-test. So it's totally fine for us to use this p-value to obtain our test result. And for instance, we have the density, the corresponding p-value for the density here is smaller than 0.5. And in this case, we can see that density is actually needed when the model has already contained the other variables. And another thing we can notice here is this degree of freedom, which is always equal to 1 because we only need to test the one coefficient. And this is actually our test statistic. I didn't mention in the nominal case, but I think here is the same. So the test statistics, which is the dropping deviance. So that's how we perform this kind of test, which is slightly different from the nominal response case, because here we only need to test one coefficient. Any questions? Okay, at last, we are answering similar problem. So if we use this ordinal response regression model, what is our prediction based on some new observations of the x variables? So if we observe those x variables, so what's our prediction? And I think the function is still the same. It's still the same by using the predict function, but what we need to do here is just to input the ordinal regression result. And then we can obtain the predicted probabilities by specifying probabilities. And this is the probabilities. And you need to be very careful here. We actually have the order. Diseased is smaller than partly diseased, and partly diseased is smaller than healthy. And you can see by using a different model, we actually have a different prediction for the probability, which is 0.88. And still similarly, because this one is largest, so the prediction of the response is still healthy. And also you can use R to accomplish this output. So that's basically the end of this topic. And I think this is new. I think for most of you, this should be new for you. So my suggestion is just to, firstly, to compare the R codes and also R output for this true modeling. And in that case, you can learn those two models very well. And if you have any concerns or any confusion about it, my suggestion is just to think about the idea